Hope you are all doing great as we are kicking it into high gear in the competition prep season for 2024. So what is the title of this video all about? Why would I not want to get my homework done? I mean, isn't that a good thing to get your homework done? Well, let's explore that a little bit. What I mean is stop trying to get your homework done. Okay, so, and what does that mean? Well, essentially, when you look at your homework as a task or a chore to complete, it's like a checklist. And we're going to get the checklist completed so that we can move on with our lives and go do the fun thing, whatever the fun thing happens to be for you. Okay. If you're approaching your homework in that way, you're not getting as much out of it as you could be. And so that's kind of what I want to explore today. And we're going to start by going to a quote from a famous person. I'm sure you may have heard of him. If you know me, I love quotes. This is a quote, obviously, from Albert Einstein. It's not that I'm so smart, it's just that I stay with problems longer. Okay, famous quote. What he meant by it mostly is that the unsolvable type problems. He just doesn't give up. He just keeps trying them in different ways and then such and such, right? Until he's able to solve them. Okay, so he solved many problems in physics in this way and came up with paradigm shifts in our understanding of how physics worked. Okay, but I want to kind of take it maybe a little bit different than he intended. Let's take our homework problems and explore them a little bit longer than we otherwise would, past the point of when we get them done. Okay, let's look at another quote too. It's from a very famous philosopher of the modern era, Ricky Bobby. If you don't know, I cannot recommend that you watch this movie. But it obviously, it's a funny movie. And there's a famous quote in it, I want to go fast. Okay. In competition math, going fast is actually very important. But in order to go fast, you first have to want to go fast. And what does that mean? What does it mean to want to go fast? Well, I mean, we can sit there going, man, I really want to be faster. Okay, great. Are you doing anything to develop the speed? Well, no, I would just like to go faster. I mean, if I could go faster, then that would be better than going slower. So I would like that. Okay, I want to. Well, what does that look like if you want to? If you want to, you'd probably work on developing it. And if you don't want to, the converse is also true. You wouldn't really work on developing it. So sometimes when you say you want something, but the actions don't align, then you're not really being intellectually honest with yourself. So now let's go ahead with that. And we're going to go ahead and jump over to a problem. And that's this problem right here. But before I go into it, I do want to mention a couple of things. The first thing is this problem comes from the Art of Problem Solving Intro to Counting and Probability from David Patrick. I wanted to stress that I do not work for AOPS. I am not paid in any way to promote their materials. They are not sponsoring this video or anything like that. I just happen to, I'm not affiliated with them. I just happen to like their materials and think they're some of the best stuff that you can use to learn the underlying concepts you're going to need on the contest. So I did take this question from there and I'm attributing it to them, and I do own the physical copy of the book. Before I dive in to explain why I chose this question, I am going to share screen to one other thing, and that's something that I get asked about a lot in my email, my current class schedule. And I'm not going to go through the whole thing. I'm going to ask you to take a screenshot, but I will cover two things. Number one, all classes have a risk-free trial. You can sit in on it. If you don't like it, you don't owe money for it. So feel free to utilize that to try the classes out to decide, is this actually going to be beneficial for me or not? Okay, so the first one I'm going to point out is the Summer Number Theory Intensive course. It's from June 24th to July 5th. It is 4 hours a day with a 2-hour break for lunch and homework in the middle. These times are Pacific Standard Time. That would be Los Angeles time if you're curious. The Number Theory Once Per Week class starts this Sunday, June 16th from 6 to 7:30 p.m. Pacific. It will not stay there forever. It's only staying in that time slot until about August, when two of the people who requested the course would be able to have the class on either Wednesday or Saturday from that point forward. So it will be at that time slot when that month comes around. These are the other classes I currently have going or I'm about to start. take a screenshot. If you're interested in those, you can reach out by email. Do check your folders because sometimes somebody somewhere labeled it as spam. And so it sometimes goes to spam folder if you do send a message and I respond in that way. So I'm going to go back now to the document here that has the question on it, and we're going to start discussing it. Okay, so how many sets of 4 consecutive positive integers are there such that the product of the 4 integers is less than 100,000? Now, the reason that I chose this question is it's not quite a standard solve process. If we ask ourselves, well, what have I learned that I can use to solve this problem? And you'll say, well, I can use Gaussian's theorem of products of 4 consecutive integers. Yeah, no, that doesn't exist actually. There isn't going to be a theorem or postulate or some formula that you were taught. Instead, you're going to have been taught a lot of ideas, and you're going to have to figure out how to utilize those ideas to the best of your ability to answer such a question faster than other people. And this problem gives you the chance to practice that. Now, if we're just trying to get our homework done, then you might just get the answer, go, oh, I got it right, therefore I've learned all there is to learn from this problem. And I'm advocating, per the quote we looked at, even though he didn't mean it in that way, that you stay with the problem a little bit longer and use problems like this to explore your ability to develop an algorithmic process and execute that process correctly and quickly in a math competition. And so you're going to have to do that later. It's good that you get the practice in now, so when it comes up, because I guarantee it will, I guarantee it will be on the test every year. They're going to ask questions no one has ever seen. And parents will often ask me, they'll say, well, why would they do that? If I take, this book and I do this test and this many tests and I practice this many hours a day, will that be enough to qualify? And the answer is maybe. I mean, we don't know. It depends on the inherent ability of the person studying, how much they remember, how well they study, how well they retain information, how well they learn, how perceptive they are, what little mechanics they learn in the process, and how well they keep that information within them and then can recall it during the test under pressure. Okay. It also depends on the questions that they're going to need to qualify, which is not going to be stuff they've necessarily learned how to do. Instead, you need to learn how to do it during the competition itself. That means you're going to know what? You know what the word for means. You know what consecutive means. You know what positive means. You know what integers are. You know what product is. And you know what less than 100,000 means. So since you know what all those means, what can you do with it? And how quickly can you do it? Okay, this also reminds me a little bit, by the way, of a class thing that I had when I was a kid. When I was in 3rd and 4th grade, they had a program called Odyssey of the Mind. Odyssey of the Mind. It's still going today. It's a wonderful program. I highly recommend that you check it out. If you have it in your grade school, you might look into, I don't think it's offered for high school students, but if you have kids that are still younger, you might see if this program is available at their school and if they can participate in it, or if you can get their materials outside of the school system. That might be possible as well. And what we would do in this group, there's about a group of 6 to 8 of us or so, and they would give us a number of objects. We'd be taken to a separate room, and we'd either make 2 teams or have one team. We all worked on things together. There was various formats for how it would work. And they'd give you something like what? They'd say, here's 12 popsicle sticks. 12 popsicle sticks. And here's 8 sheets of paper. A paper towel roll tube. Right, an empty one. Maybe they will say, here's 6 paper clips. And I don't know, some string and 2 rubber bands. And finally, a ping pong ball. And they would say, here's what we want you to do. We want you to take these objects and brainstorm a way to move the ping pong ball as far across the room as you can. Okay, as far across the room as you can. And that's it. That's the total sum of all the directions. And you're not told anything else. And so what would you do, right? And so you try to come up with some way, and there's various contraptions, and who could ever move it the farthest if there's 2 different teams. I don't know. Personally, I'd probably build some kind of tower with the popsicle sticks and a piece of paper on top of that tower, and then I would knock out the front legs and have the ball roll off the top and go somewhere. Something like that, right? But it's up to you. It's free range solving of a problem without direction. And it's a wonderful way to learn. We don't do this as often in school anymore. There are some entities that do, and I think they're wonderful entities. But this problem is a lot like that, right? Instead of 12 popsicle sticks and physical objects, we have things like 4 consecutive positive integers. We're doing a product of them, and we're trying to keep them less than 100,000. Go. Okay, so then how do you go about solving that? And why do we care about that? Why do we want to measure that on the competition? Well, think about it. This is a competition. It's going to give you some accolade, but it's also just for fun. It gives you an accolade, yes, and you can use that accolade to help yourself, yes, get into universities and things like that. It's going to help you just as much as any other award would, and it demonstrates prowess within a certain field, right? It demonstrates ingenuity and creative problem solving and innovation and things like that, right? How much you studied, how much you prepared, what you're passionate about. It can do all of those things. But why do we want to measure that? And why do colleges care? And that's because who are you? You are the next generation. You're coming up to do what? To be a part of society. You're going to be pushing society forward. You are the future. Do we want people who can only repeat the processes that have come before us? Or do we want people who will drive innovation? They will drive creativity. They will create new things. They will make a better world for humanity or for a company, right? If a company's going to hire you, well, then these are the kind of things they would look for. Do you think it's more valuable to the company, a person that gets plugged into a system, right? And it's still a valuable thing. Nothing wrong with that person, by the way. You get plugged into the system and you work within it and you go through the rule book and they say you're going to do this, this, and this on these times and these days and using these machines or what you would have you talk to these people, okay? Or do they want the person who creates the training curriculum and designs the systems, those other people or AI or machines or robots or whatever will work in? One of those two people is a lot more valuable to the company. They're no less valuable as human beings. In my opinion, everybody deserves respect. The person who works on your bike, the janitor, all of those people are wonderful humans and there's nothing wrong with them or what they chose to do for a career. Okay, so we don't want to denigrate anything like that, but we're talking strictly about the income that you might have. And if you care about that and you'd like to have financial security, then you're going to be somebody who can solve problems that no one has ever solved before. And to a degree, this test measures your ability to think in that way. So don't get alarmed by these kinds of questions and don't just finish it and get it done. Go and explore. How could I have done it faster? Where can I pick up efficiency? Okay, so that's what we're going to do right now. How many sets of 4 consecutive? Here's how you might start. You might go, take baby steps. What's the smallest positive integer, I say? Well, it's 1. So I'll do 1, 2, 3, 4. There's 4 consecutive. It's 24. Let's go to 2. 2, 3, 4, 5. There's 120 because it's equivalent to 5 factorial. Okay, do I want to keep doing this? It's going to start getting prohibitively difficult. So maybe I could do something different. Maybe instead of listing these one at a time, I could jump ahead. These are the ideas that you'll have during the contest. So you'll jump up. Where should you go? I don't know. Let's go to like 10, 10, 11, 12, 13. I'm going to go over 2 ways that you could calculate an approximation for this value. One is better, but the other one's also good and useful in other situations. I'm going to go over the less good way as far as efficiency goes for time right now, but you can explore it to use it on other problems in the future. Okay, and we'll go the more efficient way afterward. The thing I'm going to focus on is right here. I'd like to leave that 10 alone. We love 10s when we're multiplying because it's a 0 on the end. You should never think about multiplying by 10. You should say blah, 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 0 on the end. That's the way to think of it. Now, if I think about 11 times 12 times 13, I can tell you right now at a glance it is less than 12 cubed. How do I know? Well, experience. Experience exploring problems like this. So how did I get that experience? You can go back to grade school. I developed it back then on my own. No one taught me. Okay, now the materials might have been designed to help you see that. Perhaps they didn't state that directly, but maybe it was designed in that way. Let's look at how I might know this. There's problems called farmer's fence. I call it the farmer's fence principle today as a result. He's got 40 feet of fencing, she's got 40 feet of fencing, whatever it is, they have that, and they want to make a pen for their cattle or whatever, their garden, something like that, okay? And they have 40 feet, so you say, what if I made a perfect square? And you go, okay, that's 100. 10 times 10 is 100. All right, so what if I reduced it a little bit? I made this -1 and that +1, my length and my width. I would now have 9 times 11, and I would get 99. Okay, then what if I went down by 2? 8 times 12, 96, 7 times 13, 91. And you can see that the farther you get away from equilibrium, the lower the amount comes. So based on that alone, this will be a true statement. Now, it's not rigorous as a proof, but it's a demonstration to yourself of its reality. Okay, but let's get into what this is. I actually use this technique on a lot of problems. I call it centering. So if I want to multiply a number, I'll go over it in a minute, an example, by numbers that have a centered number, I'll use this technique and what I learned on my own from this problem by exploring this problem type. Why? I wanted to be faster. I wanted to go fast. And I explored as a result of that. I took action to actually create that reality. Okay. So what I noticed was even in grade school, 4th grade, 5th grade, you go down by 1, you go down by 4, you go down by 9. You also, by the way, go down -1, -3, -5 if you're going down one term at a time. And that's important too. That's another pattern. In fact, I'll tell you what to explore. Why don't you explore the sum of the first n odd integers? I'm not going to tell you how that works. You explore it. You might already know. That's great. Okay, so, but I want to go down with what's happening from the number 100. I'm going down 1, 4, and 9. What are those numbers? I say, well, they're perfect squares. Interesting. I had not learned difference of squares at that time. Okay, so I said, well, how would this work? How could I do it, right? I might say, if I'm calculating numbers like this, I could take the middle number squared and subtract the gap squared. And I call that centering. And it's used on things like, if I told you 28 times 32, I can say it's 896 in a split second. Why? Because 30 squared, the middle number is 900. The gap is 2, square the gap, 4, subtract it, get 896. Now, why does that work? What's causing it? What's the mathematical, technical proof way of demonstrating why that works? All it is really is difference of squares. And you can do it with difference of squares. I can say this number is 30 minus 2, that number is 30 plus 2. I can do difference of squares. It comes out a squared minus b squared. And that's really the underlying mechanism, right? That's actually causing that to occur. But I don't think about difference of squares on the contest. I use the fact that I know the centered number squared minus the gap between that centered number and the other two squared is going to be the answer. I just do it straight up, right? So again, what if I had something like 27 times 33, 891? I'm not multiplying this or this. I'm not thinking about difference of squares. I'm just using the technique in its most efficient, purest sense. So because I've developed that, I can spot that 11 times 13 is going to be equal to 143. There's more than one way to get that, by the way. 11's trick for multiplying. You can use that if you're familiar. You can add 1 plus 3 to get 4 and put it in the middle of the 1 and the 3. That's for two-digit numbers and multiplying by 11. Okay, but I would know at a glance that 11 times 13 is less than 12 squared. Because again, it's the centered number is 12, and they're one off of it, and it's less than it. If I multiply both sides of this by 12, it will still be less than. Okay, so all of that are things that you can learn by exploring just computational aspects of numbers. Let's clear this off. We've got the 1, 2, 3, 4. We've got all the way down to 10, 11, 12, 13. Okay, and I'm telling you that 11 times 12 times 13 is less than 1728, which is 12 cubed. How do I know? Well, an AOPS book had a problem from Srinivas Ramanujan where he used the 12 cubed in a problem, and then I happened to learn it from that, and then I've also gone ahead and memorized my first 12 perfect cubes. I recommend you do it as well. So I can say, since this is less than 1728, let's just say it's approximately 1728. If you now multiply by that, you add a 0 to the end. How close am I with this to 100,000? I am quite far away, not even close. So because of that, I just make a pit stop at this number and move on. But now I'm going to go over the more efficient way to do it. The more efficient way would have been to say, this is approximately 10 times 10 times 10. Or even better estimate might be the 11 to the fourth, because it's in one, and that's down one, up one, and stuff like that. What would 11 to the fourth be? Well, luckily, it's going to be, 14641. Okay, how do I know that? It's part of Pascal's triangle. The first 5 rows of Pascal's triangle are all multiples of, or powers of 11, their exact value. Okay, so I don't memorize 11 to the fourth, but I do memorize several rows of Pascal's triangle. Okay, but for now, let's just stick with the tens because it's really easy on the brain. It's just 10 to the fourth, 1 with 1, 2, 3, 4 zeros. We're not even close. And it's a close enough estimate that because you're so far from 100,000, it's fine. We don't care that it's 7,280 off or something like that. We're just going for rough estimate because that's going to get you the speed that you need. And so the next thing that you're going to do is you're going to say, well, how far can I go? Let's go up and use the same method on 20. 20 times 21 times 22 times 23. If I take 20 to the fourth, it's like 2 to the fourth with 4 zeros. And that's definitely less than this. And this is way over 100,000. So we would know at this point that you've gone too far, right? And so you're going to say, all right, well, if 20 is too far and 10's not even close to far enough, but it's kind of balanced around that 100,000 a little bit. I mean, sure, this is actually probably over 200,000 to be honest, but they're going to probably balance around there. So maybe I should try something in the middle, like 15 times 16 times 17 times 18 and 16 times 17 times 18 times 19. Okay, and to some extent, you're going to go, isn't this just guess and check? Yes. Yeah, there's nothing wrong with guess and check, right? Your school teachers don't want you to do it. They want you to solve with the process. But you get to do whatever you want on the task. Go ahead and do that kind of thing. A lot of problems on AMC you explore by doing guess and check and see what you learn, right? And you're just trying to get a feel for the problem and then pick up your speed towards the efficiency at the end because you want to go fast, right? This is your playground to develop the skills to go faster on the contest. So don't neglect this kind of stuff and have fun exploring these types of problems. Let's look here. I'm going to go with this because I like 15 as a multiplier. If I wanted to calculate exactly what that was, I could say that this is less than 17 cubed, and I could say that's 289 times 17, and I could say that's 17 times 300 minus 11. And I could say that's 51 with 2 zeros, and that's 187. Thank you, 11's trick. And I would take away 100 to 5,000. I would take away 87 to 4913. That would be 17 cubed. Okay. The speed at which I do that, you should honestly be even faster than. I'm talking, so I'm slowed down in my calculation. I would be here much faster if I'm not explaining anything to you. Okay, so 4913, this is less than that number because it's less than 17 cubed. And I'm just going to estimate that number now to 4,900, and I'm going to multiply by 15. How do I do that? Do I actually multiply? No, I do 10 plus 5 in my head, and all it is you're going to do times 10 and then half of that. So it would be 49,000 and then half of that, 24,500. That's how you multiply by 15. Don't think about the 5. Don't think about the 15. Do 10 and half of 10. Fast, okay? You just cut the other number in half. That's going to get you there. This is roughly 75,000. Okay, we're still not quite there yet. Let's go up to here. Do I want to do the 18 cubed thing like I did up here? No. Why? I've got 16, 17, 18 right here. That's the same block I had right there. I can use the exact same approximate value. And even if I use a closer value like 4913, and even if I multiplied by 20, which is greater than 19, I would only be at 9826 with a zero. 98,260 that would be, because the zero from the 20 is going to do that. It's basically 2 times 10. I'm doing the 2 first and then putting the 0 on the end, right? So because this is still less than, and I know that it's going to be less than that, and that's less than 20, but look at how close you are. You went from around 75,000 to right up against the barrier. We're done. The final step is to figure out how you were going to count. And if you looked at the 1 times 2 times 3 times 4 and 2 times 3 times 4 times 5, if you looked at those, the first number was counting for us. So when we get to the 16, that's the answer. And that's how you want to take your homework and explore it. Have fun with it. If you're just looking at it as a task to get done and it's just a chore so that I can make my parents happy or I can get into the college or the school, right? If that's really the only reason you're doing it, you don't have any passion for the learning, you're going to have a difficult time qualifying for the second or third round. Highly recommend you enjoy the problem, you explore things, and you look into the background and the problem-solving mechanics and develop speed on all of those things. Learn how to think on the fly, learn how to plan, learn how to make a plan with no previous problems of that type really seen or thought about, right? That's what you want to do, and that's why you want to solve many more problems. The old adage kind of works. Solve thousands of problems. Learn from the experience as you go. You're not just going to get the problem right, you're also going for efficiency. One last time, if you're interested in the classes that I teach just like this in the classes. You can send me an email. Do check all your folders because it sometimes gets sent to spam. Hope you enjoyed the lesson, and I will see you in the next video.